Hello and welcome back to this channel. Dear students, in today's session, I'll explain you how to solve numericals on the boundary conditions. We'll be solving numericals on both electric and magnetic boundary conditions. If you haven't yet watched the the video of derivation of boundary conditions, do watch that video, so that will be helpful for solving such numericals. So first numerical is two extensive homogeneous dielectrics meet on z is equals to 0 plane. Now important part is you need to draw the proper diagram. It is mentioned that two dielectrics meet on z is equals to 0 plane. So if I want to draw the diagram, then let us say this is the boundary which represents z is equals to 0 plane. So above which there will be one medium, below which there will be another medium. Then z-axis, almost in all numericals, to make the thing simple, mark the z-axis in the vertical direction like this. I have marked the boundary horizontally, z-axis is drawn in the vertical fashion. So for z greater than 0, see this is z is equals to 0, this point. For z greater than 0 means upper side, z less than 0 means lower side. For z greater than 0, epsilon r1 is equals to 4. So I will write the values in the diagram. Epsilon r1 is equals to 4. And for z less than 0 means this lower side. For z less than 0, epsilon r2 is equals to 3. These are the given values of relative permittivities. A uniform field E1 bar 5ax bar minus 2ay bar plus 3az bar kilovolt per meter exists for z greater than 0. It means that in the region z greater than 0, E1 bar exists whose equation is given. So I will draw E1 bar like this. Let us say this is E1 bar. If this is the E1 bar, why I have drawn it in the upper side? Because it is clearly mentioned this exists for z greater than 0. So I have drawn the line for E1 bar like this. Now everything like E1 bar, E2 bar, E3 bar, whatever it is, it has two components as far as boundary conditions are concerned. One is tangential component, another is normal component. Normal means perpendicular. So if the boundary is horizontal, perpendicular component means this vertical line. So along this line I will mark En1, because in this range, in this region, there is an existence of E1 bar in the upper region. So I have drawn E1 bar and En1 is marked in the vertical direction. You may well write En1 bar. Now this is for region 1. First part, find E2 bar for z less than 0. So z less than 0 means this is z is equals to 0 point. Z less than 0 means at the lower side we have E2 bar. So somewhere I will mark E2 bar like this. This is say diagram of E2 bar. If you want to mark En2 bar, naturally it will be in the vertical direction, but presently it is nowhere required. So first part let us complete. Find E2 bar for z less than 0. First I have completed the diagram. Now very important step, this E1 bar I have shown it like this. En1 is the normal component. Do remember the basics. If E bar is electric field intensity, in case of boundaries there are two terms. One is tangential component, another is normal component. So any vector, in this case E bar, is addition of tangential plus normal. So I will write E1 bar is Et1 bar plus En1 bar. That is addition of tangential component plus normal component. If you draw the diagram proper, it's very simple. En1 bar, that is normal component, is along z-axis. Look at the given equation of E1 bar. Which component is along z-axis? That is 3az bar. So I can simply write En1 bar is equals to 3az bar. Very simple. En1 bar is along z-axis. I referred the given equation. So 3az bar is the component which is along z-axis. So I have directly written En1 bar is equals to 3az bar. Now Basic equation is E1 bar is Et1 bar plus En1 bar. I have written the expression of En1 bar. Naturally, it indicates that remaining two components are related to tangential component. So, from the given equation, I can directly write Et1 bar is equals to 5ax bar minus 2ay bar. This is the tangential component of electric field, that is E1 bar. So, I have written expressions of En1 and Et1 bar. These are normal and tangential component. Now you need to refer the boundary conditions. So boundary conditions are very simple as far as numericals are concerned. So you need to mention in the exam like this: according to boundary conditions, Et2 bar is equals to Et1 bar. So this is one of the boundary conditions. So naturally, equation of Et2 bar, I will write it like this: 5ax bar minus 2ay bar, as it is same as Et1 bar. What I am supposed to calculate? E2 bar. So equation of E2 bar, if I want to write, I will write it like this: Et2 bar, that is tangential component, plus En2 bar, that is normal component. Out of this, I have already got the value of tangential component. Now my aim is to calculate the normal component, that is En2 bar. To calculate the normal component, we have to use one more boundary condition. Similar to this, I can write dN2 bar is equals to dN1 bar. This is again second boundary condition. dN2 bar is equals to dN1 bar. Now, recall the basic equation. Basic formula is D is equals to epsilon into E. Or in a more generalized form, we can write it like this: D bar is epsilon 0 epsilon r into E bar. So dN bar is equals to dN2 bar. So I can well write this as, I can well generate equation of dN1 bar as epsilon 0 epsilon r1 into En1 bar. In the exam, how you can recall these things, how you will come to know that you need to write only equation of dN1 bar? Very simple. What are the available values? We have the value of En1 bar. So anyhow, I have to express dN2, that is dN1, in terms of available or obtained values. So En1 bar is already available. So I have written this expression. Now value of epsilon r1 is equals to 4. So this can be simply written as 4 epsilon 0 En1 bar. For the simplicity, I am keeping epsilon 0 as it is. Now we have one more equation. I can well write this as dN2 bar can be written as epsilon 0 epsilon r2 En2 bar. Remember, we want equation of En2 bar, because what we want E2 bar which should contain Et2 bar, which we have, and we need En2 bar. To calculate En2 bar, I am using these tricks. So dN2 is equals to dN1. I got this equation, but we have one more formula, dN2. Why to use this formula? Very simple. I now want the equation of En2 bar. So put the value of epsilon r2. Epsilon r2 is 3. So I will write it as 3 epsilon 0 En2 bar. From this equation, I can write therefore En2 bar is equals to dN2 bar, that is this value dN2 bar divided by 3 epsilon 0. What I did, I have transferred this 3 epsilon 0 at the LHS. So it is dN2 bar upon 3 epsilon 0. Therefore, En2 bar is equals to value of dN2 bar. We have this value I am talking about, 4 epsilon 0 En1 bar. So it is 4 epsilon 0 En1 bar upon 3 epsilon 0. I have kept epsilon 0 as it is because later on it gets cancelled like this. So epsilon 0 gets cancelled. En1 bar, we have the ready-made value of En1 bar, 3az bar. So if I will put the values, it becomes 4 into 3az bar upon 3. Therefore, En2 bar is equals to 3 gets cancelled, 4az bar. Now remaining part is pretty simple. What I want to generate equation of E2 bar. It is ET2 bar plus EN2 bar. We have got the value of EN21 bar. So it is E2 bar is equals to ET2 bar. Put the value. It is 5 AX bar minus 2 AY bar. I have used this value. Plus EN2 bar. EN2 bar is plus 4 AZ bar. So this is the answer of first part. I have calculated value of E2 bar for Z less than 0. The second part is angles E1 and E2 make with interface. That means in simple language we have to calculate angle made by E1 bar and E2 bar with the interface. This is the interface. This is the boundary. So I have denoted the angles by theta 1 and theta 2 in the diagram. To make the calculation simple, we know that this is a perpendicular line, this is a horizontal line. So total angle between them is 90 degree. So if I want to write this angle will be 90 degree minus theta 1. Same way, let us say I have drawn the perpendicular. Same way, here this angle is theta 2. This is again vertical line, horizontal line, so total angle is 90 degree. So this angle will be naturally 90 minus theta 2. Now, using simple geometry, if I want to express the angle like this, cos 90 degrees minus theta 1, I am referring this diagram, is equals to, it can be written as E1 bar upon this line hypotenuse upon En1, that is adjacent line, because I am writing equation of cos of this angle. So E1 bar upon En1 bar, but this is the angle, so we need to write magnitude mod of E1 bar upon mod of En1 bar. I have written all the expressions for the reference. So mod means, how will you be calculating it? Under root of this square plus second term square plus third term square. So it is 5 square plus minus 2 square plus 3 square. This is mod of E1 bar divided by mod of En1 bar. We have the equation of En1 bar, that is 3 AZ bar. So it is under root of 3 square, this magnitude square. So naturally square root and this under root sign gets vanished. So if you solve this equation, I mean if you want to write it further, this is the equation for cos 90 minus theta 1. Therefore 90 minus theta 1 is equals to cos inverse of this entire term. So if you solve this, you will get answer of theta 1. So theta 1, how to solve it? By doing the calculations on the calculator, you will get value of 90 minus theta 1. Then simply calculate theta 1 by using this formula. So answer of theta 1 will be 29.12 degrees. This is the angle made by E1 bar with the interface. Same technique we will be using to calculate theta 2. So how to write the expression of theta 2 like the previous case? Cos of 90 minus theta 2. I am talking about this angle, which is E2 bar, that is mod of E2 bar. Since it is angle, I need to consider mod of E2 bar, this line divided by this value. This value is naturally En2 bar, because every vertical line which is along z axis is normal component. So it is mod of En2 bar. Simply put the values. I have written the expression of E2 bar. So mod means under root of first term square, second square, third term square. So it is 5 square plus minus 2 square plus 4 square divided by En2 bar is 4 AZ bar. So under root of 4 square. Simply you may write 4. If you solve this, you will get value of theta 2, that is 36.6 degrees. So these are the answers of theta 1 and theta 2, that is angles made by E1 and E2 with the interface. Now the third part is, it is asked to calculate energy densities in both dielectrics. The basic formula, basic notation of energy density is W to the base E, which is formula is 1/2 epsilon mod E bar square. So this is the basic formula. We know that epsilon is epsilon 0 into epsilon r. If I want to calculate energy density for medium 1, it is WE1, which is equals to 1/2. Epsilon is epsilon 0 into epsilon r1. Value of epsilon r1 for medium 1, I am talking about medium 1, is 4, and mod of E bar. In the last part itself, we have calculated this value of mod of E bar and its square. So it is square root of 5 square plus minus 2 square plus 3 square and square of this. So naturally square root gets cancelled. One important part you need to take care about is the unit of E1 bar is kilovolt. We need to convert it into volt, and this is mod of E1 bar square. So it is 10 raised to 3, and due to square it becomes 10 raised to 3 square. Unit is kilovolt, I need to convert it into volt, and this is mod E square. So it is 10 raised to 3 bracket square. Put the value of epsilon 0, epsilon r, that is epsilon r1 in this case, which is equals to 4. So if you put the values, directly you will get the answer. WE1 is 472.904 microjoules per meter square. Micro means 10 raised to minus 6. So this is the answer of WE1. Same way, if I want to calculate value of WE2, same formula I am referring, 1/2 epsilon 0 epsilon r2 into mod of E2 bar. In the earlier case, here I used the formula of E1 bar. Now E2 bar is this equation. So same way, if you just put the values and do the calculation on the calculator, epsilon r2 is again 3. Simply put the values like the previous case. This answer will be 597 microjoules per meter square. So this is the way how to calculate the different components as far as the electric boundary conditions are concerned. What are the possible variations in the numerical? Only one or two parts can be asked. I have covered all the three parts to get the clear-cut idea about this thing. Or in some numericals, diagram can be given, so it becomes again more simple. If diagram is not given, to make the things very simple, draw the boundary like this and always keep z-axis as a vertical axis. Then from the given information, you will have to decide whether E1 bar should be above this, I mean at the positive side of z-axis or at the negative side of z-axis. For example, in this case it is clearly mentioned z greater than 0. That means E1 bar is at positive z-axis. Then z less than 0, there epsilon r2 is mentioned, so it is on the negative side. That means E2 bar should be at the negative side. So this is the way how to solve boundary condition numericals on electric field. Now let us solve one numerical based on boundary conditions for magnetic fields. The next numerical is the xy plane. Do remember this wording. Xy plane is same as z is equals to 0 plane. Serves as interface between two medii like the previous sum. For z less than 0, mu r is 6. That means there is one medium for z less than 0. While reading the numerical itself, we will draw the diagram. This is the interface, which is very much similar to the earlier numerical. Then, as I mentioned in the last numerical, draw the z-axis vertically. This is z-axis. Above this is say z is equals to 0 point. Above this, we have positive value of z, that is z greater than 0. For z greater than 0, mu r is 4. So I will write here mu r is equals to 4 for z greater than 0. This is mu r. Mu r is relative permeability, because this is the problem of magnetostatics. And z less than 0 value is given as mu r is equals to 6. So z less than 0 means lower part along negative z axis. So this is mu r is equals to 6. These values I have written. If interface carries a current, this is the value of given current 1 upon mu 0 AY bar milliampere per meter, and B2 bar is given as 5x bar plus AZ bar milliwebers per meter square. Now, the question arises, which medium should I consider as B1 bar and which medium should I consider as B2 bar? Now, to make the thing simple, how to correlate the things, which is medium 1 and which is medium 2. Read the question, whatever information is given first, I will consider it as a medium 1. So z less than 0, mu r is 6. Z less than 0 means this lower side. So for z less than 0, that means at this side, I will say it is medium 1. So mu r 1, I will denote its value is given as 6. Naturally, remaining medium is medium 2. So this is mu r 2 and its value is given as 4. From the given information itself, I have considered z less than 0 as medium 1, z greater than 0 as medium 2, and accordingly I have written the values in the diagram. Since now this is the medium 2, I will mark the given vector, given value is B2 bar, so I will mark B2 bar like this. This is the direction or vector of B2 bar. Naturally, if you want to write mark value of or direction of B1 bar, it will be like this. It is in medium 1. So this is the way how I have drawn the diagram. Now B2 bar is given, unit is milliweber per meter square. Keep in mind this unit is milliweber per meter square. Whenever required, we need to we'll convert it in terms of webers per meter square. And one more thing, current is given as 1 by mu 0 A y bar. Presently we will keep it as it is. It is asked to calculate H1 bar and B1 bar. So from the given information, refer the diagram. This B2 bar is in medium 2. Related to this, always the vertical line or the component which is along z axis is normal component. Since it is B2 bar, I will mark this normal component as Bn2 bar. Very simple. B2 bar is in this medium. Related to this, whatever component is there in the vertical direction, that is along z axis, is normal component. So Bn2 bar. From the given equation, this is the given equation of B2 bar. Look at the equation. This component is along z axis, so directly I can write Bn2 bar is equals to 8az bar. Very simple. Whatever component is along z axis, that is the normal component. Notation in this case is Bn2 bar, which is 8az bar. So remaining component must be tangential component. So this is tangential component, that is Bt2 bar is equals to 5ax bar. This is the tangential component. Now after this you need to apply the boundary condition. So according to the boundary conditions for magnetic field, Bn1 bar is equals to Bn2 bar. We know the value of Bn2 bar, so it is same as 8az bar. Next part, what is asked in the question? It is asked to calculate H1 bar and B1 bar. First we will think of H1 bar. See, Bt2 bar, this value we have. Now we have the basic formula, B is equals to mu H or B bar is equals to mu H bar. Therefore, I can write H bar is equals to B bar upon mu. Therefore, HT2 bar is equals to Bt2 bar upon mu 0 mu R2. Very simple. I have written the basic formula. Since available value is the value of Bt2 bar, I have used everywhere suffix 2, because from the available value first I need to calculate HT2 bar, then we will think how to calculate H1 bar. So simply put the values. Bt2 bar is 5ax bar upon, I am keeping mu 0 as it is, mu R2 value is 4, so it is 4 mu 0. So it is 1.25 upon mu 0, 5 by 4 is 1.25 into ax bar. This is the value of HT2 bar. But I need H1 bar, that means I need value of HT1 bar and HN1 bar. To calculate value of HT1 bar, because I need finally to calculate value of H1 bar, so we need to calculate the value of HT1 bar, we need to make use of the boundary condition. So you need to remember this magnetic boundary condition. HT2 bar minus HT1 bar is equals to K bar. What is K bar? K bar is denoted or called sheet density. That is simply the value of current density which is given in the question, 1 by mu 0 AY bar milliampere per meter cross AN bar. AN indicates the normal component. Normal component, as the way how we are drawing the diagram, will be along z-axis. So if I will put the values, I will get the things like this. HT2 bar, value of HT2 bar, I have this value 1.25 upon mu 0 AX bar minus HT1 bar. I am keeping it as it is. K bar is given value of current density 1 by mu 0 AY bar cross. As I mentioned, AN bar is always along z-axis as per this diagram. So AN bar is same as AZ bar. Remaining part is AY bar cross AZ bar. This answer, cross product of Y and Z, AY bar and AZ bar, is AX bar. So I can well write the next equation as 1.25 mu 0 AX bar. Do remember, this unit is milliweber, and again the value of this current density is milliampere, so I am not making any conversion. Minus HT1 bar, which I am keeping it as it is. I need to calculate it. 1 by mu 0 AY bar cross AZ bar is AX bar. Therefore HT1 bar, simply rearrange the terms. So if I will transfer HT1 bar at the RHS, it becomes plus, and I am writing it as a first term. So I am transferring this over here. Then 1.25 by mu 0 AX bar minus 1 by mu 0 AX. This direction is AX bar, so it is AX bar. Very simple. I have transferred this HT1 bar at the RHS, and this term is transferred at the LHS, and then sides are interchanged. Therefore, from this I will get HT1 bar is equals to 0.25 upon mu 0 AX bar. This is the value of HT1 bar. We have calculated the value of HT1 bar. To calculate H1 bar, I need, this is the tangential component. Naturally, I need normal component. That is, I need the value of HN1 bar. Then HT1 bar plus HN1 bar will be H1 bar. So, how to calculate HN1 bar? We have this equation, BN1 bar, that is BN2 bar is 8AZ bar. Refer the basic formula. B is mu H, rather mu 0 mu R H. So, B bar is mu 0 mu R H bar. I want HN1 bar, so from this I will write it like this. H bar is B bar upon mu 0 mu R. Therefore, if I want to obtain HN1 bar, do remember this suffix is 1, so it is BN1 bar upon mu 0 mu R1. Refer the diagram, mu R1 is 6. So it is, and value of BN1 is 8 AZ bar upon mu 0 into 6. So it is 1.33 upon mu 0 AZ bar. This is the value of HN1 bar. Now basic formula, HT1 bar is equals to, or directly I will write the answer, H1 bar is equals to HT1 bar plus HN1 bar. We already calculated value of HT1 bar. So this equation can be written as this value 0.25 upon mu 0 AX bar plus 1.33 upon mu 0 AZ bar. This is the answer of first part, that is H1 bar. Now remaining calculation is more simple. What I want value of B bar. So this is the value of H1 bar. So from this, from the basic equation, I will write B1 bar is mu 0 mu R1 into H1 bar. Therefore, B1 bar is equals to mu 0. Value of mu R1 is 6 into 6 into, I will write all the things in the bracket, that is 0.25 upon mu 0 AX bar plus 1.33 upon mu 0 AZ bar. Again, if you take mu 0 common and outside this bracket, these terms gets cancelled. So simply 6 into all these values. So final value, final answer will be B1 bar is 1.5 ax bar plus 8 az bar unit. I haven't made any conversion, so unit remains milliweber per meter square as it is. So this is the final answer of B1 bar. Dear students, I have explained the numericals on both the things, electric and magnetic field. So the possible variations are, again in this numerical, apart from this calculation, it can be asked to calculate, to find out the angle made by B1 bar and B2 bar with the interface, which is pretty similar like the last sum. So that's it for today's video. If you like this video, don't forget to smash the like button. Thank you very much.